of whatever we had done in organic chemistry. So the first thing, so just it's going to be quick. I'm not going to write notes for this. We've already kind of gone through this, but kind of very quickly. So the first thing is it starts with carbon. Carbon has 4 electrons in 4 orbitals. So those 4 electrons, when carbon is bonded to 4 different atoms, like 4 different hydrogen atoms, the 4 electrons, they get pulled in different directions. And that is known as sp3 hybridization. So the carbon's orbitals, they get stretched in different directions. And you just give them new names. That's it. That is sp3 hybridization. So when they get stretched in different direction, there is no 2s, there's no 2px, there's no 2py, and there's no 2pz anymore. The spherical and the dumbbell-shaped orbitals, they change their shape. And you start calling all of them sp3 hybrid orbitals. That's tetrahedral, and all the angles are 109.5. We were more interested in sp2 hybridization, where carbon is only bonded to 3 atoms, which means that it's making, so 3 atoms, 3 of the electrons around carbon, they get pulled in 3 different directions. Whereas the 4th electron, the 4th p orbital, kind of remains unchanged, and we can mark that. So this 4th orbital, this p orbital, it remains unchanged. The other 3, they change their shape. So carbon is usually bonded to just 3 atoms. And this was what had happened in alkenes. In ethene molecules, carbon is only bonded to 3 atoms. So 3 electrons get pulled in different directions. They form sigma bonds. And the 4th orbital, which is the p orbital, the other carbon also has a 4th electron, which is the p orbital. They end up forming pi bonds because they are parallel to each other. And they end up forming these pi bonds. And in alkenes, the electron density is really high because the electrons are delocalized. The electron cloud is present between the 2 carbon atoms, which means that the electron density is really, really high. So we then started talking about alkenes because alkenes are the closest molecule that's close to benzene. So we did all the bromination reactions, like alkenes would undergo bromination. They will undergo hydration. Water will get added. The double bond H and OH will get added. Hydrogenation, that is, hydrogen gas molecules would get added to it. So you'll have these hydrogen atoms that will get added to it. And there was a 4th one, which was hydrogen halides, where you had an HCl molecule, and HCl molecules, atoms H and Cl, would get added. Now, the next thing was the mechanism for electrophilic addition. The mechanism was that in all these electrophilic addition reactions, you had a bromine molecule, which would get polarized. It wasn't polarized before, but because of the electron density over here, because of the double bond over here, the electrons in the bromine atom, they would get repelled. They would be repelled to the other side, which is why that one would become slight negative and the other one would become slight positive, which would be even more strongly attracted to the double bond. So, and this is what's going on over here. There's a high charge density, which has large polarizing power. The pi bond has a large charge density, which is why no special conditions are needed. Bromination happens on its own. The bromine atom, like one of the bromine atoms, the one that I'm marking here, it goes and the bromine, which is positive, it goes and bonds with takes away the electrons from the double bond, and a carbocation is formed. The other one, which is Br negative, would then come in and join with the carbocation. So you got a carbocation intermediate, and you have to remember this mechanism. And then there was this Markovnikov's rule, which was that when you have unsymmetric alkenes, the H atom, like in HCl, in H2O, etc., would always get attracted to the carbon that is already bonded to more hydrogen atoms. And the reason was, the H positive has a choice. It could bond with this carbon atom or it could bond with this carbon atom. And the thing is that the H atom likes to bond with the carbon that's already bonded to more H atoms. And the reason for that was that this other carbon would become a carbocation. But if the carbocation is in the middle, then it's surrounded by large groups on all sides. So its positive charge is kind of smaller because it can pull electrons from all sides. But if the carbocation formed is right at the end of the chain, like that's a primary carbocation, which means that it's bonded to more hydrogen atoms because it's at the end of the chain, then that carbocation would have a large positive charge because it's not surrounded by large groups. It's right at the end of the chain. So this one would be unstable. What that basically means is that the positive carbocation would have such a large positive charge that it would not let H take those electrons in the first place. Because the H was coming in, taking the electrons from the double bond. So the positive charge would be so large that it's not going to allow the H to pull those electrons in the first place. So this would be a minor product. It would be very difficult to form this carbocation because H will not be able to steal the electrons. But over here, the carbocation would be formed easily because the carbocation would have a small charge, positive charge, because it's surrounded by large groups. TK, is this clear?
Yes, sir.
And you have to remember this, that carbocation having more alkyl chains which are electron donating, their positive charge density decreases on the carbocation, and carbocation is considered to be more stable. So this one is more stable. So you should know what the Markovnikov's rule is. The next thing is we started talking about benzene and we talked about the skeletal formula. Cambridge CIE doesn't use, this is not CIE, but it's a good way to think about benzene. It's basically 6 carbon atoms that are all sp2 hybridized. They're all making double bonds. So it's like alternating double bonds. But what happens is that the double bonds kind of mix up, which is why you have this electron cloud over here. This is what happens. That in benzene, every carbon atom, like if you look at this carbon atom, and if I look at this carbon atom, this one, then this carbon atom is, so this carbon atom is bonded to 3 atoms. The 4th electron is available. And each carbon atom is identical. It's bonded to 3 atoms. On one side, it's bonded to an H. On the other side, it's bonded to 2 carbon atoms. So there's always 1 electron that's available. Now, what happens in this case is that the electron that is available, they would all start forming pi bonds. So the pi bond would be kind of delocalized. The p orbital would not only be overlapping with the carbon on the left, but it would also be overlapping with the carbon on the right side, which means the electron density is lesser. So all p orbitals overlap and a delocalized pi electron cloud is formed above. So it's like a big double bond where all the electrons are mixed up. So this is known as sp2 hybridized. The electron density is lower compared to pi bonds and alkenes, as electrons are delocalized over a much bigger region, less polarizing power. So the electron is overlapping on both sides, which is why the negative charge density is very different compared to a normal double bond, which we had drawn earlier. So you got a normal double bond, the electron density is a lot higher because the p orbital is only overlapping with the p orbital on the left side. And this p orbital is only overlapping with the p orbital that's on the right side. So they're not all over the place. But in benzene, the p orbitals kind of mix up and they're all over the place. TK, is this clear as well?
Yes, sir.
So then the thing was that this is what we discussed, that you got a single bond, you got a double bond. Benzene bond is kind of somewhere in the middle. I mean, the ring that you draw, this ring represents something that's between a single bond and a double bond. Then we talked about the only reaction that mechanism that we need to study, and that's electrophilic substitution. So the reaction was simple, that if you add bromine to it, a bromine will substitute one of the hydrogen atoms, and if you add Cl2 to it, it will go and substitute one of the H atoms with a Cl. And HBr and HCl are your byproducts. But the thing is that you need a catalyst for this, which is FeBr3 or AlBr3 or FeCl3 or AlCl3, depending on which one you're talking about. And the mechanism of the reaction was that a bromine molecule, which is non-polar, when it reaches close to a benzene electron cloud, it gets polarized. But the polarization is weak. The positive charge and the negative charge are not really that strong. The positive charge is small, and I can write that it's kind of a small. So it's kind of a small positive charge. So it's not that interested in the electrons in the benzene. It won't attract the electrons in the benzene that strongly. So the polarization is really weak, and because of the low electron density of the pi electron cloud, because it's all over the place. So the negative charge is too spread out. So you need a catalyst in this case. FeBr3 is your catalyst. The reason you need a catalyst is that the Fe over here is going to pull the electrons from the other side. So on one side you've got benzene, which is pushing the electrons. On the other side you've got Fe that is pulling on the electrons. So we want to polarize the bromine molecule so that the bromine becomes more positive and it becomes more interested in these electrons. Eventually, what will happen is that bromine will become interested in these electrons, and what it will do is it's going to steal one. So it's going to steal one of the p orbitals and bond with it. So your pi electron cloud becomes electron deficient because the carbon that had a p orbital over here, that electron, the p orbital that's missing over here, that eventually went to bromine, and bromine bonded with it. So carbon right now is, one of the carbon is now sp3 hybridized. So because all four are now involved in bonding, there's no pi bond anymore. Whereas the rest of the electron cloud is intact, but it's electron deficient because it's positively charged because bromine took its electrons. And in the next step, the H loses the electron. So the carbon atom over here gets its electron back and the pi electron cloud reforms. So this is what is going on in the reaction. Is this clear as well? Zoha, Minail, is this clear, Abdullah?
Yes, sir.
Yeah. Yes, sir.
So all reaction mechanisms would be very similar to this. This is electrophilic substitution. You need an electrophile for that. And so this is the mechanism that you're going to draw in your exam. You got a benzene. Bromine gets polarized, but you need FeBr3 so that it becomes polarized even more. The positive bromine gets attracted to the carbon atom over here. So a carbonium ion or the benzene gets a positive charge. And let me just quickly Google this. Can I refer to this as just one second. Carbonium is a carbocation. I forgot the name of the benzene with a positive charge. So I don't think it has a name, probably no. Benzenium ion, no, that's definitely not that. It's actually, I think it's called a, forget the name. It's called a benzenium ion. The C6H7. No, just a second. Forget the name. I don't think it's ever going to, and they're never going to ask you that. So this one is, I mean, just remember this as benzene having a positive charge on it. I just confirm because I've never actually heard of iridium ion. That's so you forget I think we can safely ignore this. So anyways, coming back to this. So it's the same mechanism, except this is the one that you're going to draw in your exam. The H loses the electron in the next step, and the benzene electron cloud becomes complete again. DH then bonds with the Br over here and forms HBr. Now moving on, there was another reaction which is exactly the same, and that is nitration, which is for nitration. Remember the two reactions. One is with Cl2 and Br2. That's with FeCl3, AlBr3 catalyst. The other one is nitration, where you use concentrated nitric acid and sulfuric acid, and the temperature is around 55, and an NO2 gets attached to benzene. Now, in this case, what you have is, you need to remember this equation. What the equation suggests is that the first thing is nitric and sulfuric acid. They're going to react and they're going to produce a nitronium ion, which is NO2 plus 1. And then that NO2 plus 1 is going to act as your electrophile. It's going to go to benzene, borrow one of the electrons. So the benzene electron cloud would be complete everywhere except for that carbon atom. And then H loses the electron and gives it to the benzene to complete its outer shell. And in that way, your structure was, the NO2 is going to get attached to it. So NO2 plus 1 comes in. So it's exactly the same mechanism as the other one, except you don't have you don't show a catalyst over here, but the other thing is that the mechanism is the same. Positive bromine gets attracted to the carbon atom, and in the next step, H loses the electron to the positive benzene. And similarly, you had these reactions. You had Friedel-Crafts Alkylation, which is kind of the same. The previous one was nitration. So it kind of has the same mechanism. You need AlCl3 or FeCl3 catalyst. Alkylation is you got a carbon chain with a Cl in it. So the carbon with the Cl is the one that's positively charged. So the positive carbon is going to be interested in the benzene over here, and it's going to go and attract, it's going to get attracted to the benzene and bond with it. You don't need to know the mechanism. The only thing you need to know is that the positive carbon atom is going to bond with it and the Cl will get knocked out. So the positive carbon atom will bond with it and the Cl will get knocked out. So that's Friedel-Crafts alkylation. The other one is Friedel-Crafts acylation. So this is alkylation as well. You got a benzene and you got a molecule which is a halogenoalkane and it's got a positive carbon atom. The positive carbon atom is going to be attracted to this one. So the Cl will get knocked out and it would eventually form HCl. No need to remember the mechanism, except that that particular carbon is the one. It's always this carbon that's going to get bonded to it. And similarly, you have acylation. In acylation, you've got acyl chlorides, which are acetyl bond ON, Cl. In that case, what happens is the carbon has a pretty strong positive charge. So since it has a pretty strong positive charge, it's going to be attracted to benzene and the Cl gets knocked out. So the carbon with the double bond O is going to eventually bond with it. And that's acylation. I mean, we can try and do another mechanism like this. So here's my benzene, and I'm going to react it with so let's say there's CH3 and there's another CH3 and there's a Cl over here. And this carbon has a strong positive charge. So remember this, that it's always going to be this particular carbon atom that's going to be attracted to the benzene. It's the positive carbon that's going to be attracted to the electrons in benzene. So when the product is formed, the product would kind of look like this. So when the product is formed, what you'll have is you'll have a benzene, and it's going to be this carbon that will bond with it, and the Cl will get knocked out. So it's going to be CH3 on one side. It's going to be another CH3 and another CH3, and the Cl will get knocked out. So this one is alkylation actually, and we can similarly do acylation, which would be similar to this. So we can do another one, which is going to be acylation, that you have a benzene. And let's say it reacts with so in this case, you got this carbon, which is positive, and the benzene is going to be attracted to this positive carbon atom, and the Cl will get knocked out. So the same thing would happen. You'll have a benzene, and this thing is going to come in without the Cl. So the positive carbon is going to come in, and it's going to eventually bond with the benzene. And in this case, usually means ketones are going to be produced. Cl bond O would come in the way. Is this clear?
Yes, sir.
So we did acylation, we did alkylation, and we did, so remember there are 4 reactions, and what we can do simultaneously is I can start, just so that we can remember things. What I can do is we can start with the chart as well, so that we know what's happening. So this one over here, so you can start with a chart, and I think I got this benzene, and I'm going to write the 4 reactions that are taking place. So I've got, I mean, I can turn it into I can turn it into 4 different things. So So first thing, it could be turned into, you can add a Cl to it. Or you could add NO2 to it. Or you could add a carbon chain to it. Or you could add acetyl bond O to it. So this is the four reactions that we've studied so far. And let me. So that's one, just a second. So four different reactions, and we can add in the conditions now. So this one is Cl2 plus AlCl3, or you can have FeCl3. That's the first one. This one over here is nitration, so that is concentrated sulfuric acid and the temperature is 55 degrees centigrade. For this, you would need a halogenoalkane, which in this case would be CH3. And the catalyst. And this last one would be an acyl chloride. And for this, you would need a catalyst as well. still we studied these 4 reactions, and you should know the mechanism of each one of the reactions. All of them are electrophilic substitution. So all of them are electrophilic substitution. This is electrophilic substitution. This one as well is electrophilic substitution. This one is also electrophilic substitution, and this one as well is electrophilic substitution. So I'm going to keep building on this chart. That's the first thing. You should know the mechanism of this reaction. I'm going to put a tick with the reaction whose mechanism you should be aware of. That's one is this one, and the other one is this one. You don't need to know the mechanism of either. How do you get this thing? So no need to know this. So no need to know this mechanism and the other 2 mechanisms. And I'm going to add another one over here, which would be, we can talk about bromination separately, which is kind of the same thing. And the conditions for that were BR2. Or AlBr3. Those are going to be your catalyst. And this one is also electrophilic substitution, and you should know the mechanism. So with Cl2 and with the Br2, the reaction is kind of the same. For the other ones, for this one, you should know the equation as well. And we've got acylation and alkylation. So those are all your benzene reactions. TK, is that clear?
Yes, sir.
So TK, let's continue. Next time we'll just try and build this chart, TK, because remember in organic chemistry, it's more about, remembering the mechanism is one thing, but it's more about knowing what happens, what are the reaction pathways and what are the conditions. So we'll try and build on this, and we'll try and build on the 2,4,6 directing groups and the 3,5 directing groups. TK. So we'll do that on Monday then. TK.
Okay, sir. Okay, sir. Allah Hafiz.
Okay, Allah Hafiz. Take care.
Thank you.